This is how the molecular spectra looks like. In front of you, you have molecular spectra of ethyl benzene. Please observe that spectra. You can zoom into the spectra and observe it. Now, I hope you must have noted the molecular ion peak. You must have noted the base peak. When this is the base peak for M by Z value 91, it means this is the ion which is most stable, and this is your molecular ion. Now also observe these peaks, small peaks. We will see what are those peaks. Okay, so these smaller peaks, they are called as M plus 1 peak, M plus 2 peaks, and M minus 1 peak. We will see what those peaks are. So ethyl benzene, molecular mass of 106 Dalton. The analyte vapor was bombarded with a stream of electrons that led to the loss of electron by the analyte and formation of molecular ion M plus, like this. You get this molecular spectra. The charged species of ethyl benzene plus is the molecular ion. Relaxation occurs by fragmentation of part of the molecular ion to produce ions of lower masses. So higher mass molecular ion will produce lower mass ions. The positive ion produced on electron impact are attracted through slit of mass spectrometer, where they are sorted according to their mass to charge ratios and displayed in the form of mass spectrum. The largest peak is termed as the base peak, which is over here. This is the base peak. If you will see, its intensity is considered as 100. This is another example, CH2, Cl2, dichloromethane. You can observe that at value 84, you have got the molecular ion peak. At 49, you have got base peak. Please also note that there are these small peaks. Observe this molecule, you get molecular ion at 88, but look at the height of the peak, it is very small. So it means molecular ion is not stable. Okay, so let's come to those concepts M plus 1, M plus 2, and all that. See, sometimes peak occur at masses that are greater than that of the molecular ion. We have seen that. These peaks are attributed to ions having the same chemical formula but different isotopic composition, like in case of this molecule, methyl chloride. See, there are possibility that there is C12H1Cl twice, both of atomic mass of 35. The other possibility that C12 is replaced by C13. Other possibility is one of the Cl is replaced with Cl37. Another possibility, there is one C13, there is one Cl37. And next possibility, both chlorines are 37 and you have C12 here. There will be one more possibility which will be extremely rare, where you have both chlorines as 37 and carbon also 13. Okay, so extremely rare possibility, but that is also possible. See, if you change the atomic mass of carbon and chlorine that is forming the molecule, you can see you have got lots of variation in the mass of that ion, mass of that molecule. So these are M plus 1, M plus 2, and so on peaks. Okay, the size of the various peaks depends upon the relative natural abundance of the isotope. Relative natural abundance means, see, rarely both the isotopes are present in the equal quantity. Okay, the relative abundance of different elements and their isotopes is given in this table. Go through the table. Okay, so isotope peak rules. When the parent compound contains an element that has more than one stable abundant isotope, more than one peak will be formed for each fragment containing this element. Although nearly all elements occur naturally as a mixture of isotopes, for higher elements of interest in organic chemistry, hydrogen, carbon, nitrogen, oxygen, one isotope, which is the lighter one, predominates. That is very clear in this chart also. Okay, see, for carbon, if you will consider, or for nitrogen you will consider, for oxygen if you will consider, you will see that relative abundance of the lighter molecule is more. Okay, now this one example of the calculation is given. I am sure you must have done that in your BPharm, so I am leaving this part for your self study. Let's go to the metastable ion concept. Now, metastable, meta word means something less than. Okay, uh, so metastable is relatively less stable. So what happens is the molecule gets ionized, forms one ion. That ion enters the analyzer part of the machine, but in the analyzer it gets degraded. Okay, in analyzer it gets degraded. The original ion which which was formed, it may be suppose having mass m1, and after degradation in the analyzer it got mass, reduced mass as m2. Okay, so you will get a diffused peak like this. Okay, a broad peak like this, whose value will be equal to m2 square divided by m1. Okay, now these metastable ions are formed during 10 raised to minus second, that is time spent between the electrostatic and magnetic analyzer. This is the generally time ion spent in the analyzer. Are quite broad but provide direct information about ion reaction. Immediately you will come to know that there is some chemical reaction that is happening. There is more information of metastable ion, but it is basically talking about the stability of the metastable peak. Let's move on to the instrumentation.